Ever wonder why you'd weigh less on Mars, even though it's a planet? Or why a hypothetical planet twice the size of Earth might actually have less gravity? We're about to unlock the cosmic secrets behind these gravitational mysteries. The answer lies in one of the most elegant equations in physics, G equals sine gm slash r squared. Let me break that down in plain English. The small g is what we're after. The acceleration due to gravity, the pull you feel standing on a planet's surface. The g is a universal constant and has a fixed value throughout the universe. The capital M is the planet's total mass, and small r is the distance from the planet's center to its surface, its radius. Now here's where it gets interesting. Mass pulls you in. Radius pushes the effect away. What I meant to say hmm, is that gravity follows what we call the inverse square law. What does that mean? It means that if you double your distance from the center of mass, the gravitational force doesn't just halve BUT, it becomes 1/4 as strong. And when you triple the distance, the force becomes 1/9. It falls off very fast. This is why that r square in the denominator is so powerful. Now let's imagine that we magically inflate Earth's radius to twice its current radius, but keep all the same mass. What happens to surface gravity? You're now standing twice as far from all that mass. The distance is doubled, so r squared becomes 4 times larger. Since mass stayed the same but r squared quadrupled your weight, the surface gravity drops to 1/4 of what it was. Same mass, bigger planet, less gravity. Now let's go the other direction. Take all of Earth's mass and compress it down to half its current radius. You're now standing closer to all that matter. The radius halved, so r squared becomes 1/4. Divide by a smaller number, and surface gravity quadruples. You'd weigh 4 times as much. Same mass, smaller planet, more gravity. Mars has about 11% of Earth's mass, much lighter. But it also has only 53% of Earth's radius, much smaller. When you run the numbers, small g on Mars equals sine 0.19, m underscore Earth 0.53, r underscore Earth squared. The small radius partially compensates for the low mass. Mars doesn't end up with 11% of Earth's gravity. It has 38%, about a third. That's why astronauts on Mars will bounce around but not float like they would on the moon. This is exactly why neutron stars are so deadly. Take a star's worth of mass and compress it into a sphere just 20 kilometers across. You've got enormous mass packed into a tiny radius. The result? Surface gravity so intense that if you dropped a marshmallow from 1 meter above the surface, it would hit with the force of a nuclear bomb. Let's now do the same calculation for our moon. The moon, by the way, has only 1.2% of Earth's mass and 27% of Earth's radius. Do the math and you get 16% Earth gravity, hence the bouncing Apollo astronauts. Here's the beautiful part. This same equation works everywhere. On the smallest asteroid, on the largest star. Whether you're calculating the orbit of Mercury or the fall of an apple, it's the same inverse square law, the same dance between mass and distance. So here's what you need to remember. Gravity at a surface isn't just about mass. It's not just about size. It's about the relationship between them. Mass divided by radius squared. More mass means stronger pull. Greater radius means weaker pull, and powerfully so because of that squaring effect. And that's why you can't judge a planet's gravity by its size alone. You need to know two things: how much stuff it has, and how far that stuff is from where you're standing. The universe, as always, is more subtle than our first guesses. It's not the biggest planet that has the strongest pull. It's the one that knows how to pack its mass tight. And that's the gravity equation. Thanks for watching and subscribe for more videos.